Research and Publications Committee at IIM Ahmedabad. I'm delighted to welcome you all to the RNP, or the Research and Publications virtual workshop series that we are running. We have a very good audience here, about 50 of us. So this looks very good. Today's topic of the workshop is heuristics to solve optimization problems. And the workshop today will be conducted by Professor Diptesh Ghosh. So we are all really pleased to welcome you, Professor Ghosh, and thanks for making time to run this very important workshop. Professor Ghosh, as many of you already know, all of you in fact will know that he's a professor in production and quantitative methods area here at IIM Ahmedabad. A very brief background about Professor Ghosh. He's a fellow of IIM Calcutta and he completed his BTech from IIT Kharagpur. Professor Ghosh is a former faculty of IIM Lucknow and he completed his postdoc at the University of Groningen. Professor Diptesh Ghosh is widely published in this field in leading journals, including Computers and Operations Research, the European Journal of Operational Research, and other important outlets. And his interest, among other things, involves the use of meta-heuristic methods and mathematical programming in solving complex problems and in decision-making in general, with a wide array of applications. So welcome again, and very pleased to have you, Professor Ghosh. So, you can talk about the terms of how you want to run the workshop, how audience can participate, when they could ask questions. So it's entirely up to you. So I won't waste any more time. So this is over to you.
Thank you, Professor Chakravarti. So it's a little strange calling you Professor Chakravarti, but since we are formal, so we are going to remain formal. Thanks, Professor Chakravarti, and for this kind introduction. And welcome to all of you who have joined on this Monday afternoon. So what I'm planning to do is to have a tutorial on heuristic methods for solving optimization problems. That is as the name of my talk suggests. Now, I will be staying away from formalism and math as much as possible. The idea is to give you a broad overview of the different heuristic and meta-heuristic methods that are usually used in solving optimization problems. Now, most of the work that I do is in the field of combinatorial optimization, which is just a fancy way of saying that I deal with 0-1 problems. So in the problems that I study, every problem has a bunch of components and you form solutions by either picking or not picking a solution component. So that is the combinatorial nature of the problem. So as you would remember from your basic math, the number of ways in which you can pick and choose components among a group of components, what you know as permutation and combinations, it's usually a very large number of solutions that are admissible, and finding the best solution out of that seems to be a difficult problem in many cases. So that is what I'm going to talk about. I plan to talk about 2 hours, so with a break in between. I really don't know when the break will come, but I will, it would be around at the 1 hour time point. It may be slightly ahead or slightly behind 1 hour, depending on how we proceed. Now, if you have questions, then there are 2 kinds of questions that you could have. You could have clarificatory questions where the question that you are asking is directly related to the slide that I'm presenting at that point of time. In that case, I would request you to raise your hand. I would see that your hand is raised. I would ask you to state your question and try and answer it to the best of my capability. Now, there are certain other questions which are not directly related to whatever I'm presenting right then, but of a more philosophical nature. So I would request you to keep those questions till the end of the tutorial, after which I would be able to take those questions without fear of overrunning my time. Okay. So with this, let me start with the tutorial. So I'll share screen and hope that you can see the screen here. Wait a second, let me do a little bit of fixing up. Okay. Okay, so so now, if you're talking about optimization problems and combinatorial optimization problems in general, we have known for a long time that combinatorial optimization problems, if you look at it, can be broken up into two types of problems. Some problems are called easy problems and some problems are called hard problems, right? There is, of course, a bunch of problems whose complexity status it's not known. It's not known whether they're easy or whether they're hard, and the only way to do that is to prove one way or the other. Now, both these types of problems exist in multitudes. So for instance, if you're looking at easy problems could be linear programming as an easy problem. Finding the shortest path between 2 points on a road network is an easy problem. Finding a minimum spanning tree, which would be a way of connecting several points in a network with the least amount of road connecting them, is called a minimum spanning tree problem. That's an easy problem. If you have a list of elements, searching whether or not an element exists within that list is an easy problem. So these are some easy problems. On the other hand, you have other problems called like the general integer programming problem, or a knapsack problem, or a traveling salesman problem. These are called difficult problems or hard problems. Now we call a problem easy or difficult depending on how the time required to solve such a problem scales up as the problem sizes increase. So for instance, let's take an easy problem. If we talk about the shortest path problem, this shortest path problem is something that all of you use very regularly. A place where you would use the shortest path problem is whenever you want to find out how to go from one location to another location using Google Maps. So for instance, right now I am located at IIMA Ahmedabad. So let's call this IIMA Ahmedabad. And let us suppose that I want to go to a nearby destination, let's say Sabarmati Ashram. So I ask Google for directions, and this is the amount of time that it takes to tell me how I can go from my current location, IIMA Ahmedabad, to Sabarmati Ashram right here, right? Note the amount of time that it took to answer my question. Now, when I'm answering this question, the road network that Google is considering is the road network of Ahmedabad, specifically Western Ahmedabad, right? Now, let us scale the problem to a much higher level. So let us say that I'm sitting at IIMA Ahmedabad and I want to visit my parents who are in Kolkata. Okay, so let me type out my address in Kolkata. So if I type out my address, I ask for options and I've got it. So if you notice that right now, the network that Google is searching is the the network of roads across the whole country. And even if you don't want the whole country, it is looking at the network over this whole area, right? Which is much, much higher than the network when it was looking only at Ahmedabad. The point is that when it's doing this, it is also not trying to simplify the network. For instance, if I go to, let's say, Prayagraj, which is on the way, if I zoom in on this, you will find out that within Prayagraj, it is not telling me that, okay, go through Prayagraj. It is actually giving me the road directions to go from inside Prayagraj, which is Allahabad, and on my way to Bidhannagar in Calcutta. So you see, these are problems where even though the problem size has increased tremendously, the time required to solve the problem does not increase all that much. Okay. On the other hand, let us talk about something which is a hard problem. Let's talk about the traveling salesman problem. This is a problem which you would face, for instance, if your local supermarket has a delivery service. Now, if you're looking at a supermarket like Big Basket, the Big Basket every day would have a bunch of locations in which to deliver their items. So every time they have a truck or a van which decides to with which they decide to supply various locations, and they have to find out the shortest route by which they can supply all these locations and come back to the original point. So this problem is called a traveling salesman problem. Now, this traveling salesman problem is much harder. So for instance, if you're talking about the shortest path between 2 points which on a network which has, let's say, 50 junctions, the whole thing can be done in less than a second. But if I have a network and if I have 20 odd points where I have to figure out how to visit those 20 points, in what order to visit those 20 points and come back to my base location at Big Bazaar, then what you'd find out is that takes several minutes to solve. Now, when we took the shortest path problem and changed the network from the network of a city to the network of a region of the country, then the amount of time it took to solve that larger problem was marginally more. But if I take this same guy and say that, okay, you do not have 20 locations to deliver, you have 30 locations to deliver, the problem actually becomes a lot more difficult than when it had to deliver to 20 locations. The time required to solve that problem would be much higher. So therefore, when I talk about a difficult problem, I mean a problem where if the size of the problem increases, the time required to solve that problem would increase dramatically. Okay, and in our language we call it the time increases exponentially. Okay, so of course, even though these problems are hard, these problems are regularly solved in practice. Okay, so whenever you have a routing problem, more often than not you talk about traveling salesman problem. Now, if you are a big basket or if you are a big bazaar, then you are not going to talk about only one van which is going to serve all your customers. You will have multiple vans, and the first thing that you would have to do is to take your locations, divide it into subsets so that each subset is dealt with by a single van, and then look at which vans and the routing of the vans. So this kind of a problem is called a vehicle routing problem, which is a slightly more complicated version of a traveling salesman problem, right? Now, if you look at a supermarket, and if you look at the racks of a supermarket, then the problem of deciding which product to put in which location of the rack, right, is a problem which is called a layout problem. And this layout problem is also a difficult problem. So in fact, many of the problems that you see in real life are actually difficult problems that are difficult to solve, right? So what do you do when you're faced with such a problem? You finally have to solve the problem. So to do that, there are two ways that people talk about. One way is that they frame the problem as a mathematical program. So a mathematical program is a special way of writing down the problem so that you can feed it to a software like Cplex or Gurobi, which can come back with a solution by following some proprietary methods. Okay. Now, those softwares are extremely good softwares, and for mid-sized problems, they can give you an optimal solution pretty fast, right? But however, if your problems become very large, then sometimes the amount of time required by, say, Cplex or Gurobi itself is very large. Okay. In that case, what you want to do is to find out specific algorithms to deal with specific problems. So for instance, if you have a traveling salesman problem, you want to devise algorithms which will take care of traveling salesman problems and no other problem, right? So those are kind of algorithms, they are called exact algorithms. These algorithms are normally used to solve large size problems in reasonable time. However, there are two issues with these problems also. Now, when the size of the problems increase and as time passes, you will normally, for any problem, you will find larger and larger instances of those problems to solve. Now, as soon as the problem sizes increase, these specialized algorithms also start taking a pretty long time. Not only that, the specialized algorithms are specialized for a very, very narrowly defined set of problems. For instance, let us talk about the traveling salesman problem, which our big basket or big bazaar is going to use to route its van. So if I'm talking about that problem, then a normal assumption that such traveling salesman problems take is that if you have 2 points A and B, then the distance from A to B is the same as the distance from B to A, which is very natural. The other thing that you would also always want to say is that if I have a direct path from A to B, the time taken through that direct path is less than the time taken if I go from A to some other point C and then come back to B. So these are very commonsensical results that you would expect from a traveling salesman problem. However, think about this. This is something that you've seen very often. Now, if you have a road, let's say it's going from where you're currently there to that junction out here. If you're going from that junction to this junction, you run into traffic jams. However, if you're going from this junction to that junction, then the road is clear. So therefore, the distance, or in case of big basket, the time required to go from a point here to that junction is much less than the time required to go from this junction to our point. So the whole assumption that if I go from A to B, the distance or the time taken would be the same as if I go from B to A is violated. Now, sometimes what happens is that here at this junction, you want to come to this place right now, and you know that there's a traffic jam. So what do? You take a take a long cut. You go to some other point through a less congested route and then using another less congested route come here. So in doing so, the time that we take to go from this point to this point is much lower than less than the time that you would have taken on this direct route. So therefore, in such a situation, you would see that my second assumption that if a direct route from A to B is shorter than a route that goes from to another location and then comes back, that also gets violated. Now, when people talk about traveling salesman problems, what they do is that they talk about problems which are symmetric, which is that the distance from one point to another point is the same as the distance from this point to this point. And they also say that the problem that obeys a triangle inequality, which means that the direct route is shorter than a route which is indirect. So in many cases, what happens is that an algorithm that you have for a particular type of problem does not quite work when you have a practical problem. So practical problems throw a lot of spanner in the classical way a problem is defined. But there's no point giving up on that, right? So for those kinds of problems, and specifically when you have a problem which is time sensitive, which means that if you are going to find out a route for big basket, you can't start in the morning and get a route late at night. You need to find a route which is immediate. Now, when you find a route that is immediate, there's a possibility that you are not going to find out the optimal route, the best route. You are quite okay if you find out a route that is good enough, which is better than what you could have done by hand, right? As long as you find it quickly enough so that you can go about your business. And that kind of a shortcut to a good solution, if not an optimal solution, is a heuristic. Okay, so right now we will be talking about different types of heuristics that are available for us to solve combinatorial problems. So if I summarize things, you know that a heuristic is a fast method. It is a fast method which gives you solutions which are not guaranteed to be optimal. An exact method is a method that gives you solutions which are mathematically elegant, which are computationally elegant, and will give you an optimal solution. Heuristics are not such methods. Heuristics are methods which you use to solve practical problems fast. So since the biggest plus point for a heuristic is that it's fast, you do not use heuristics for easy problems. Heuristics only come into the picture when you're solving hard problems. Right. So in the rest of my talk, I'll be talking about two types of problems, both of which are hard problems, and they are these two problems. One is the knapsack problem, and the other is a traveling salesman problem. So what is a knapsack problem? A knapsack problem, it's often described in a very interesting manner. It says that suppose you're a thief, okay, and you have a knapsack which is a certain weight that you can carry, okay, and you go into a shop, and each of the elements out there, each of the items in the shop have labels which tell you, okay, this item can be fenced for so much money, and the weight of this item is so much. Okay, you have that labeled all over. Now, what you want to do is to fill your knapsack up to the weight capacity with elements such that you get the maximum profit by fencing those items. Which elements would you choose? Right? In a business context, let us suppose that you have a bunch of projects. Each of the projects will give you a certain amount of profit. You can find out the net present value of the profit, and you know the cost of each of the projects, right? And you're given a budget. Now the question is, which of those projects would you choose so that you don't exceed your budget, but you get the maximum profits from those projects? So that's the knapsack problem. The traveling salesman problem, of course, we have discussed that. Traveling salesman problem is that you're given a set of points and you're given the distance between each pair of points. Now, your job is to start from any of those points, visit all the other points, and come back to the first point. You should not be visiting any point more than once. You should not leave out any point. So you have to visit every point exactly once, come back to the original point, and the total distance that you travel has to be the minimum. So that's your traveling salesman problem. Okay, so these are the two problems that we are going to talk about. Now, both of these problems are hard problems, which means that given a problem, given a set of elements, it is not guaranteed that you'll be able to find out that subset which has the maximum profit within a particular budget. You're not going to find that very easily. You're not guaranteed to find that very easily, right? So even in a traveling salesman problem, if you're given a set of points, it's not guaranteed that you're going to find out the optimal tour for that set of points. So these are two problems where we are going to talk about heuristics. So let's talk about heuristics. When we talk about heuristics, the first kind of heuristics that people used are what are called construction heuristics. Remember, construction heuristics were the game when you had some computational capabilities, but you did not have a very large computational power at your disposal, far less than the computational power that any computer has at the current moment. So what you could do is that you could do limited computations, and with your limited computations, you needed to come up with a good solution, okay? So since you had limited computational capabilities, finding the optimal solution to many of these hard problems was beyond your capability. So let's suppose you had a knapsack problem. Let's say that I had this kind of a knapsack problem where I had 9 elements, which I'm labeling E1 through E9. And these are the profits of each of the elements. These are the costs of each of the elements. And I have a budget of 90. My job is to find out a subset of these elements so that my sum of profits of the elements chosen would be the maximum, and I would not have exceeded my budget by choosing those elements, right? So to do so, the first thing that I would say is that let's try and relax this problem. And before I relax this problem, let me give you a sneak preview of the optimal solution. The optimal solution is here. Okay. Now, if you forget that this objects had to be integer valued, so you could either pick or choose, pick an object or not pick an object. Let us suppose I allow you to pick a part of an object, fraction of an object. Any idea how you would find out what is the best combination of objects that you would choose to fill your knapsack? This is the point where in a class I would call somebody, but I'm hoping that somebody would respond. Okay. Yes, Sumit and Rohit have already told me. The first thing that you would do is that you would take these elements and say that, listen, I want to fill my budget. So anytime I have my budget, I want to fill out portions of that budget which will give me the maximum profit per portion of the budget I fill. So what I would do is that I would take each of these elements and find out a ratio of profit to weight. Okay. So a higher profit to weight ratio means that that's a better use of my budget than another element which has a lower profit to weight ratio. So if I do this, first I would do is that I would reorder the elements. So when I reorder the elements, this has the highest profit to weight ratio and this has the lowest profit to weight ratio. So after this, what I would do is that I would pick up element E9 that takes up 13 units of my budget. Then E6, I've used up a total of 29 units. Then I go here, here, here. And after this, you would find out that I only have 11 units of budget left over. Now, none of these will go into 11 units. So what I'll do is that I'll take the maximum, among the remainder, I'll take that element which has the maximum profit to weight ratio and take 11 by 17 out. Okay. The whole, it gives me 18 units of profit if I have the whole 17 costs of 17. I only have 11 units of it. So I'll take 11 by 17th of the whole unit and then get a total of 11/17th of E8 and E9, E6, E2, E3, E5. If I look at the whole thing, this gives me a profit sum of 127.65, which is more than the 118 that I talked about, but that is because I've violated my restriction of either picking an element or not picking an element. Now, if I was left to either pick an element or not pick an element, this is what I would do. I would pick this, pick this, pick this, pick this, pick this. And then I would say that I have 11 elements. I have 11 units of budget left over. None of these will go, so I won't pick any of this. And that will give you a profit sum of 116. Not bad. Now, my optimal profit was 118. And to solve that problem, I would have taken a pretty long time. This is all that is required is just sorting these elements. So if I have n elements, the time complexity of sorting those elements is n log n. So in n log n time, I could have sorted these elements and then run through the elements from the left to the right and found out this thing with a profit sum of 116. So that's not bad. Now, given this, we know that this heuristic seems to be working well. Is there any way in which we can figure out? Okay, so before we figure out anything else, this is a pseudocode for the heuristic. I arrange all elements in non-increasing profit to cost ratio. Then I start off with my greedy solution as empty. And then for each element in that non-increasing profit to cost ratio, I find out if the cost does not exceed my residual budget. I put it into the element, reduce my residual budget, and otherwise I go ahead until I find out, until I go through all the elements, and then I return the solution that I have been building. Now, obviously, the question is how good or bad this kind of a heuristic could be. Now, before we know how good or bad it is, we need to find out a way in which we can figure out how good or bad a heuristic is. Now, if you have an optimal solution, if you have an exact algorithm that gives me the optimal solutions, I know that the solution I would get is the optimal solution. Then how good or bad that optimal algorithm would depend on how much time it is taking. Here in a heuristic, I'm not even sure that the solution that I'm getting is an optimal solution. So therefore, one way of figuring out how good or bad a heuristic is to talk about something called the performance ratio of the heuristic. So if I talk about the performance ratio of the heuristic, I just say that, okay, given a particular problem, if zk star is the optimal solution value, optimal profit sum for that problem, and through my heuristic, I've got a profit sum of ZKH, then ZKH by ZK star would be my performance ratio. So in this case, what happens is that the performance ratio is 116 by 118 because my greedy solution had a cost of, had a profit sum of 116, and I know that my optimal solution has a profit sum of 118, right? So now that is for this problem itself. Now, when we talk about how good or bad is the heuristic, we do not take one problem instance in mind, we talk about all problem instances. So therefore, if we consider the set capital K of all knapsack problems, then the worst case performance ratio is the minimum of this ratio over all problems. Now, conceptually, that's something that we can grasp. But if I have to find this ratio, then I have a problem. There is no way that I will evaluate the greedy algorithm for all the kinds of all possible knapsack problems. I can't do that because the total number of knapsack problems is infinite. So what would be a way of doing things? The way would be to look at the problem from a logical perspective and then find out what kind of problems are there for which the greedy heuristic will perform badly. Okay, so here is one type such instance. Let us suppose that I have a knapsack problem with just two elements, E1 and E2. E1 has a profit of 1 and a cost of 1. E2 has a profit of 999 and a cost of 1000. So if I rank them in profit to weight ratio, which comes first? E1 has a profit to weight ratio of 1. This has a profit to weight ratio of 0.999. So obviously E1 would be the element that would be considered by the heuristic, by the greedy heuristic. So it will put E1 in the bag. So once it puts E1 in the bag, how much budget will it have left over? 999. Can it put E2 in this bag? It can't. So therefore, in this kind of a problem, the greedy algorithm will output a result, a profit sum of 1. Now, what is the optimal profit sum? The optimal profit sum is, of course, this solution, which has only E2 in the bag, and that profit sum is 999. So if I have a problem which looks like this, the worst case performance ratio is at least 1 by 999. Okay? What we can do is that we can try this a little, take this a little further and just say that take a sufficiently large value K. And let us suppose that the profit of E2 is K, the cost is K plus 1, my total budget is K plus 1, and the first element still has profit of 1 and cost of 1. So in this case, you would find out that the performance ratio for this problem, for the greedy algorithm, is 1 by K. And as K increases, the performance ratio goes down. So in the limit, the performance ratio would be 0. So the minimum of this value, the worst case performance ratio for the greedy heuristic is 0, which means that a greedy heuristic can do arbitrarily badly for knapsack problems. This is a result which is correct theoretically. Practically, this is practically useless because if you look at greedy heuristics, if you do a computational experiment, you'll find out that the greedy heuristic typically gives you a value between 90% and 99% of the optimal solution. So in practice, the greedy heuristic is a great heuristic. But if we are going to look at something like the worst case performance ratio, then the worst case performance ratio for greedy is arbitrarily bad. But even then, this is one of the ways in which you evaluate how good or bad a heuristic is. The other way to evaluate how good or bad a heuristic is to take an average case performance ratio, where you would find out the expected value of ZHK over ZK star over all knapsack problems. For that, you would have to make assumptions about the data from which all this set of knapsack problems comes from, and your solution, your results would be based on the assumptions of that data. And therefore, many of these methods, though theoretically very sound, are practically not very useful. Okay. Usually, when you are looking at heuristics, you are looking at their empirical performance. Okay, so in which case a heuristic, the greedy heuristics empirical performance is great. Now, since the worst case performance ratio of greedy is very bad, there is a very nice and neat trick which actually solves that issue. If you find out, so the way to do that is, and I'm not going into details here, the way to do that is to just take the output of the earlier greedy, compare it with the profit of the highest element, the largest profit element in your problem, and then just output the better of the two. If you do that, you'll find out that the worst case performance ratio increases to 0.5. Okay, now look at this kind of a heuristic. Now, if you had a knapsack problem is a hard problem. So therefore, the time required for solving the knapsack problem was exponential in the size of the knapsack problem. On the other hand, if you're looking at this greedy solution or the fixed greedy solution, the time required is order n log n, which means that it is done in a jiffy. So if you have a knapsack problem with, let's say, 10,000 elements, an exact algorithm will take you several hours to solve it, whereas this thing will take you less than a second to solve it. Even if you are not willing to spend several hours solving the problem, you're certainly willing to spend more than a fraction of a second to solve the problem. So for instance, let us suppose that I have 5 minutes to solve the problem. So would I stick with this? Because I obviously cannot go and solve the exact problem. So the next question that people have is that, okay, if I have a little more time, can you think of some heuristics which will give me better solutions if I had a little more time that I can allow them? Turns out that for some problems, like the knapsack problem, you can do this. So let's see how you do that. What the kind of problems that we are going to talk about are what are called approximation schemes. So to do that, what you would do is that you would take all of these problems and then take a look at these problems. If you look at these problems, you'll see this guy has very high profit. This guy has very high profit. This guy has very high profit. The rest of the profits are less than the profits of these three elements. So what I'll do is I will divide the set of elements into two groups, a set of big elements and a set of small elements. Usually you would prefer the set of big elements to be of small cardinality. Now, what you would do is that you would compute different combinations of these big elements. So I can say that I will not choose any big element, or I can choose only element E2, or I can choose only element E6, or I can choose only element E8, or I have E2, E6, or E2, E8, or E6, E8, or I have all of them. So if you have k elements in your big elements, you have 2 to the power k different ways of combining these elements. Now, whenever you have this combination, there will be two things that could happen. One, this combination would have a total cost which is more than the budget, in which case you throw out that combination. If the combination has a profit sum which is less than the budget, then you take that combination and fill the remaining budget greedily with the small elements, right? In other words, you do this. You divide the elements into two groups, B for big and S for small. B has high profit elements, S has other elements. Start out with nothing. Then you create a set of all subsets of these group B whose cost sum does not exceed the budget. And for every element here, you obtain a solution in which you add the elements of the small elements into that big element subset using fixed greedy. Okay, take a large subset of the larger elements and fill the remaining knapsack with the small elements using a greedy method, right? Now, when you've done that, find out the best solution that you get out of those. Now, why is this method different if you have different times? So if you have less time at your disposal, this group, capital B, would have very few elements, right? If you have more time at your disposal, the group B would have larger number of elements. So as soon as the cardinality of B increases, the number of groups with which you will have to do this thing is going to increase. So if you have a lot of time, you would put all elements in the big group B, in which case what you will do is that you will find out all different combinations of elements that are possible and then choose the best, in which case you'll have the optimal solution. Okay, if B has all the elements, then your performance ratio is 1. You always get the optimal solution. If you have almost no time, then you keep B empty, in which case you will just get the solution from fixed KD, and your worst case performance ratio would be 0.5. Now, if you have more elements, the more the time you have, the more the elements you keep in capital B, and the more you move from here to here. Okay, the more your worst case ratio improves. And what you would see is that if you are talking about this, you're talking about a very fast heuristic. If we are talking about this, you're talking about a very slow heuristic. And if you have an intermediate amount of time, you're talking about an intermediate heuristic. Okay, so this is a way in which if you have more time, you can get better solutions. Okay, now let's change tracks to the traveling salesman problem. Now, if you talk about a traveling salesman problem, you have a whole bunch of cities or points or nodes, and what you want to do is to create a tour out of it. So as we said, this is one of the classically difficult problems, which means that to get an optimal solution is very, very difficult. So what you do is that you run heuristics. So what heuristic would you run? The first heuristic that comes to mind is something like this. You look at all these points and you find out which points are closest to each other. So you see 6 and 8 are closest to each other, join them. So when you join them, you have formed a part of the tour with 2 endpoints. One is 6, one is 8. Now you look at every other node and see what is the distance of those nodes from 6. You also see what is the distance of those nodes from 8. Thereby, you find out a city or a point which is closest to one of the endpoints. Then you join them with that endpoint. So I've joined them. So now my partial tour is here. Now I look at all these other points, find out which one is closest to either this point or this point. Whichever is the closest, I join that point. So I join this point. After I join this point, the next point I'll join is here. After this, I see that the closest to this endpoint is 0.3, the closest to this endpoint is 9. And then suppose it turns out that this is closer to 8 than this to 2. Then I'll join this point. I'll keep on joining them till I have joined all the points, and then I have only one way to complete the tour, which would be to join 7 and 9. Okay, so when I do this, the heuristic that I'm talking about is a nearest neighbor heuristic. So for every subtour, I find out the neighboring point which is closest to the endpoints of the subtour and join that, right? This is what it looks like. Let's not get into this. The other thing that we can do is another heuristic called an insertion heuristic. So here again, we look at these points and find out which points are closest to each other. So these 2 points are close to each other. Now, what I would do is that I would join 8 to 6 and 6 to 8. So this forms a closed tour, but it does not include all my points. So then I look at all the points and find out which is the point that I can add to this 6 to this small tour, so that I get a tour with 3 points, but the total distance that is covered by the tour is the minimum. So in other words, if I look at all of this, I can see that this point 1 can be connected to this subtour that I have of 6 and 8 in the cheapest manner, or no, 4. So I see 4 is connected by the cheapest manner, so I connect 4 like this. So once I connect 4 like this, then I look at point 1 and see where would I connect point 1. I can connect point 1 by removing this, adding 6, 1 and 1, 4. I can connect 2 by removing this, adding 2, 4. I can connect this by removing 4, 8 and joining this way. So I do that and I find out that this is the best way. This is the cheapest way in which I can add one more element to the tour. I keep on going this route, and at the end, I would come up with another solution. Okay, so this kind of a solution is called a cheapest insertion heuristic. Okay, so that is your cheapest insertion heuristic. Now take a look at these heuristics, and then with these heuristics, you would also see that the way you compute these heuristics is much faster than solving the optimal solution, the traveling salesman problem to optimality. So a natural question would come, like, if you had an approximation scheme for knapsack problems, can you find out an approximation scheme for these problems which will be taking a little more time than these kinds of solutions do, but would be giving me better solutions? To do that, what you would try is, but when you want to do that, you come up with a bad news, which is, it is mathematically proved that unless a very unlikely thing happens, it is extremely unlikely that we will have a solution where you suggest how far away you want to be from the optimal, and I give you a heuristic that will give you a solution that is that far away. Okay, or in other words, it's either in these kinds of heuristics, it is either a one-shot heuristic which will get you a solution, or you go for the optimal solution. There's no way of changing these kind of heuristics, making a construction heuristic that will move from the level of these heuristics to an optimal solution. Okay, so with that bad news, we are ready to proceed to the next type of things that we want to do. To see what we want to do, let us take a look at the heuristic tours. So if you have a heuristic tour like this, which was the output of my shortest path, nearest neighbor heuristic, you can see that I can make small changes in this tour and come up with a better solution. So maybe this would be a better solution. So I could take initial solution and then tweak it to form better and better solutions, and thereby go towards a good solution to my original problem. That will again not be an optimal solution, but will be a better solution than the solution that these construction heuristics provide. So for that, what I will be doing is going for something which is called an improvement heuristic, right? Quick example of another starker example of how, I mean, my nearest neighbor heuristic may not be doing the best that I want it to do. For instance, let us suppose that I have two sets of points, one set of points lying like this, another set of points lying like this. So this one lives, all the points are on this line. Here, all the points are on a slightly elevated line. And the way I have made these points is that the distance between this point and the next point on the other line is shorter than the distance between this point and this point on the same line. Okay. So if I run my nearest neighbor heuristic, the shortest and the closest two neighbors are these 2 points. So I will get these 2 points joined. After this, the next thing I will do is this. And then I will keep on doing like this. And at the end, here I have nothing to do but to join this point and this point. So this is what my nearest neighbor heuristic will output. However, if I look at another solution, then this solution will be a much better solution than this solution. So obviously, this kind of a solution can be obtained through this kind of a solution by minorly tweaking my initial solution. And that is where we have solutions where we start off with an initial solution and try improving that solution. Okay, so that is the next part of this talk, where we'll be talking about improvement heuristics, right? Now, currently, if you are looking at improvement heuristics, and improvement heuristics heuristic takes a lot more computational effort than the heuristics that we have talked about. And therefore, currently, since we have a large amount of computational effort at our disposal, most of the study, most of the research on heuristics is based on improvement heuristics. Okay, and yes. So in the last part, we are talking about formalizing methods by which we could take a solution that a construction heuristic gives us and improve it to get better solutions. Now, the good part about most of these methods that I'm going to talk about is that it does not require us to know a whole lot about the problem that we are solving. Okay. These methods that we are talking about, these improvement heuristics that we are talking about are called meta heuristics, which means that they give us a framework of implementing heuristics that work for most combinatorial problems. So the structure that I will talk about will be a general structure, and you can use that structure to come up with heuristics which will improve the construction heuristic solutions that you have got for your favorite problem. Okay, to show that, what we'll do is that we'll talk about the structure and then we'll use that structure on the two problems that we are talking about, the knapsack problem and the traveling salesman problem. Okay, so let's talk about the first heuristic that we talk about. The first heuristic that we talk about is something called local search. So the basic premise of local search is that for any optimization problems, the problem makes sense if we have multiple solutions, one or some of which will be optimal solutions. Not only that, it assumes that for every solution that you have for a particular problem, there is a way in which I can distribute those solutions to the problem such that some solutions are in some way closer to a current solution and some solutions are farther away. Okay, so the way to do that is as follows. Let us suppose that we have a solution to a problem. Every dot that I have out here represents a solution. So let us suppose that this red dot marks the current solution that I have for any problem, and this would be the output of some construction heuristic. Okay, and now this solution is just one solution among a whole bunch of solutions that are possible. So for instance, if I'm talking about a knapsack problem, the current solution that I might have is a solution which will put elements 2, 3, and 4 into the knapsack. And I might have a solution which will put nothing in the knapsack. I might have a solution which will put only element 1. I might have a solution which will put element 2 and 3. So all of these are different solutions to my knapsack problem, which I am representing in this kind of a grid fashion. Okay. Now, when I represent this in a grid fashion, then what I can say is that I can talk about a bunch of solutions which are close to my solution. Okay. So by some measure, what I can say is that this solution is close to this solution and this solution is not close to my solution. Now, what I define as close to my solution may vary. So I can talk about these 4 solutions, which I can obtain by going vertically up, vertically down, one step to the left, one step to the right, and call that as my neighborhood, or those solutions as close to my current solution. I can also talk about 4 solutions which are diagonal from my current solution and say that these are close to me. Then this solution is not close to me, but this solution is. So every time I define what solutions are close to my solution, the set of solutions which are close to my solutions is called the neighborhood of my solution. Okay. Now remember, this is a general description. I'm not talking about what I mean by neighborhoods. My neighborhood here is just those solutions which are close to my solution, current solution. Each of the elements in my neighborhood are called my neighbors. And how do I define this neighborhood? I define this neighborhood by something which I called a move. A move actually tells me how I can transform my current solution to my neighbor, right? So for instance, if this solution was the solution where I would put 2, 3, and 4 in the knapsack, and this is a solution where I put elements 1, 2, and 4 in the knapsack, I can define my move as one in which I pick out some element which is not in my knapsack, I pick out some element which was in my knapsack, interchange them. So here, element 3 is the element that I've picked from inside my knapsack. Element 1 is an element which I've picked from outside the knapsack. I put element 1 into my knapsack, take out element 3 from my knapsack, and thereby I reach another neighbor. So I can take element 1 and put it in the knapsack, remove element 4 from the knapsack, and I would have element 1, 2, and 3, which would be another neighbor. So therefore,
what I would do is that I would take a current solution and define the neighborhood by the points, by the solutions that I can reach using specified moves. Okay. So now let us suppose we are back to our original neighborhood. So these are my 4 neighbors of my current solution. So how do I define my neighborhood here? I define my neighborhood here as the solutions that I will reach if I move 1 step up, or if I move 1 step down, or if I move 1 step to the left, or if I move 1 step to the right. Right? Now, among my neighbor, even though I might have a large number of solutions to my problem, I just concentrate on my neighborhood of my solution. If I look at my neighborhood of my solution, I can find out that, okay, among these 4 solutions that were my neighbors to this one, this is a better solution than my current solution. So in that case, what I will do is that I would throw this solution out as the solution of interest and say that I am now interested in this solution rather than this solution. So if I'm interested in this solution, what I can do is I can look at the neighbor of this solution. So if I look at the neighborhood of this solution, then I can find out that among these 4, this solution happens to be better than this solution. Then I keep moving here. From here, I can keep moving here. So you see, what I'm doing is that every solution that I have, I'm searching the neighborhood of that solution, finding out a solution which is better than my current solution, moving there, searching that solution's neighborhood, finding out which is the best solution out there in the neighborhood, move to that solution, find out which is the best solution in the neighborhood of that new solution, and keep moving. So if I keep moving, every time what I'm moving to a solution that was better than my current solution. So if you, every iteration that you perform in this kind of a method algorithm, what you're doing is that you're going from the construction, the initial solution, that is the solution output by the construction heuristic, and moving to better and better and better solutions, right? You keep on moving to better and better solutions, and then until you reach a point where you see that all the solutions that you have in the neighborhood, they are not better than this solution. So there is no way in which you can move to a better solution using the neighborhood. In that case, what I will do is that I will output this solution as a locally optimal solution. Why is it a locally optimal solution? Because I can't say whether the solution is the best. The best solution might be somewhere completely different, but I know that given the solutions that I've said are close to my solution, this solution is better than any other solution which is close to it. So any other solution that is in its neighborhood. So that kind of a method to improve solutions is called local search or neighborhood search. And this forms the basis of a whole lot of heuristics which will improve a solution that you give to it. So you see, I start out with a solution, S naught, and then while I can find out solutions which are better than this solution, what I'll do is that I will go to the best solution in the neighborhood of my current solution, find out if the best solution in the neighborhood is better than my current solution. If it is better than my current solution, I move to that neighborhood, say that no, I have not found my local optimal solution, and then repeat this while loop again. But once I have a situation where the best solution in the neighborhood is not better than the current solution, I say that this solution, I say that the output is the current solution that I have, and then return that solution output. Which if you realize is precisely what we were doing out here. So I had reached a solution which was not better than where none of the neighbors were better than this solution. So I stopped at this solution and output this solution as the best solution. And as I said, this is a heuristic. It is not guaranteed to give you an exact optimal solution, which may be somewhere else. Okay, so this is what is called local search. Now, most of the time that you would spend in local search is trying to find out the best solution in the neighborhood. Let's see why that is. Now, this local search that I've talked about is in a general format. So let us take a look at how I can find out neighbors of a problem, let's say a knapsack problem. So let us suppose I have a knapsack problem with 8 elements. Each element has a profit, Pi, and a cost, Ci. And here is my knapsack. And a solution to this knapsack might be something which looks like this. So in the knapsack, the solution, I have put element 1, 3, 4, 5, and 7 in the knapsack. The others are not in the knapsack. How do I define a neighborhood? The way I can define a neighborhood is that I can talk about an element inside the knapsack, and I can say I will throw it out. So for instance, if I take this element 3 and throw it out, I'm going to end up with a solution which looks like this. All the other elements in the original solution are in my knapsack. Only element 3 has been thrown out. Element 3 has been thrown out. Or what I could do is that I have this knapsack, I will push in some other element into the knapsack. Assuming, of course, that if I push in this element, I will not exceed my budget. So if I do that, then I can have a solution which looks like this. So the element 2, which was earlier outside the knapsack, now is in the knapsack. So both of these would be neighbors of this original solution. And if this is the way I generate neighbors by either picking some element inside the knapsack and throwing it out, or picking some element that was outside the knapsack and pushing it in, then the neighborhood that I form is called an add-remove neighborhood. So if you had an add-remove neighborhood, how many neighbors can you potentially have for any element? Every one of these elements are either inside the knapsack or outside the knapsack. So whatever happens, you can form a neighbor by changing the membership of that element. If that element was in, you throw it out. If the element was out, you throw it in. So if there are n elements, the total number of neighbors would be an order of n, right? So therefore, that is the size of the neighborhood. So if we have n elements, every solution will have a maximum of n neighbors. On the other hand, I can talk about an exchange neighborhood, exactly the kind of neighborhood that I was talking about when I was talking about the knapsack problem in our general understanding. So if this was my knapsack problem, I could create a neighbor by interchanging, let's say, element 2 and element 7. So I can interchange these two, saying that 2 comes in, 7 goes out. In that case, this will be what my neighbor would look like, right? So in the other case, what I can do is that I can take exchange element 6 and element 3 and get a different neighbor which looks like this. So every time I do this, you will find out that the total number of elements in my knapsack remains the same. In my add-remove neighborhood, for all the neighbors, the number of elements in the knapsack was 1 more than my current knapsack capacity, number of elements in the current knapsack, or 1 less. Here, the number of elements remains the same. So this is called a switch neighborhood. Okay, so there are 2 types of neighborhood that you can talk about in a knapsack problem: add-remove neighborhood and a switch neighborhood. If you look at a traveling salesman problem, I can talk about a tour of the traveling salesman problem. How do I generate neighborhoods? The way I would generate neighborhoods, one of the very, very common ways of generating a neighborhood for this tour is that you take 2 of the edges and remove them. So if you remove 2 of the edges, you are going to get 2 subparts of the tour. These subparts can be joined in by joining 2 to 3 and 5 to 6. That would give me my original tour, or I can join them like this. So 2 is joined to 5, 3 is joined to 6, which will give me a new tour, which is close to my original tour because it's just one part of my tour taken and just flipped. Okay, so this is called, I can call this a neighbor of this tour. I can also take 2 more edges and flip them and get another neighbor. If I do this, if I'm taking out 2 edges and then joining the 2 subparts that are formed, the neighborhood that I get is called a 2-opt neighborhood. This 2-opt neighborhood is one of the most commonly used neighborhoods in the study of the traveling salesman problem. Of course, you could have other neighborhoods like 3-opt neighborhood, where you take out 3 of the edges and then join the tours together. That's a little more complicated than a 2-opt neighborhood, but has a larger number of neighbors of any solution. Anyway, this is what a 2-opt neighborhood is. Another neighborhood, which is very interesting because it gives very good results when you talk about traveling salesman problems, is what is known as an insert neighborhood. The idea is as follows. So here was our neighbor and here was our original tour. Now pick one element, one node or a point in this tour. Let's say I pick node 3. I take it out of the tour. So once I take it out of the tour, my remaining tour joins the other things. 3 is out. Now I will take 3 and try and insert it in different parts of the current tour. So I can try and insert it here. I can try and insert it here, 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 here. And every time I insert them in some other place, I'm going to get a fresh tour. For instance, if I take 3 and insert it between 5 and 6, this is the tour that I get. So as you see, this is different from my original tour. This is the neighbor of the tour. I can put it here and get another neighbor. And so if I do this, this kind of neighbors are called the insert neighborhood neighbors. Right? Now, whenever I have different neighbors, how do I decide on how much time it would take to compute all the solutions in the neighborhood and find out the best neighbor? Okay, so that tells me how fast or slow my search will go. So for instance, if I look at my knapsack problems, there are 2 types of neighborhoods that I looked at. One was the add remove neighborhood, one was the switch neighborhood. If I looked at the add neighborhood, add remove neighborhood, I knew that they were order n neighbors. And every time I have a neighbor, to compute how good or bad it is, I have to add up order n number of elements, right? So if I do that, the time per iteration would come up to be order n squared. But usually when you're implementing these kinds of local search algorithms, you try tricks which will reduce this time. So once you reduce this time, the total amount of time for a local search iteration will reduce. So given a particular amount of time, you can do more number of iterations and reasonably get better solutions. So if you look at an add remove neighbor, how were we figuring out a neighbor? We were either taking one element and throwing it out of the knapsack, or taking one element outside the knapsack and putting it in. So if you look at the profit for the neighbor was the initial profit of the initial solution minus the profit of the element that you threw out, right? Which can be calculated in constant time. Or if you're taking one element and putting it into the knapsack, the total profit of the new neighbor would be the original profit of the original solution plus the profit of the element that you put in. So therefore, the time required to compute the cost of the profit of a neighbor is a constant time process. So if it's a constant time process, you would find out that time per iteration reduces from order n squared to order n. How does it help? See, if you're talking about an order n squared to order n reduction, let us suppose that I had a knapsack which had, let's say, 1,000 elements. So if I did the initial way of looking at it, I would have spent 1,000 squared, 1,000,000 milliseconds to compute the neighborhood of a particular solution. Now, if I do this, I'm going to take 1,000 milliseconds to compute the neighborhood instead of 1,000,000 milliseconds. So every time you reduce the time per iteration by an order of magnitude, your algorithm becomes that fast, right? So if you're looking at the switch neighborhood, again, it has order n squared neighbors because we can talk about every 2 elements. We can talk about one coming in, one going out. So you have order n squared neighbors. Time per neighbor is again a constant time. So this takes order n squared time. Exactly the same thing happens when you're talking about the TSP. If you're talking about the 2-op neighborhood, the time per neighbor by your naive method would have taken order n time, and a 2-op neighborhood and has order n squared neighbors, right? So the total time that would it have taken it would be order n cubed. But if you look at a 2-op neighbor, so from this I'm coming to this 2-op neighbor. So what does it do? Remove this element, add this element, add this element. So essentially removal of two edges and adding two edges. So therefore, every time I want to compute the cost of a 2-opt neighbor, I can take the original cost and just in constant time find out the cost for the neighbor. So similarly, exactly the same thing happens if I'm looking at an insert neighborhood. I take out this element, I take out this element, and then I add 5 to 3, I add 6 to 3, I remove 5 to 6. So again here, the total time that I will take is a constant time, and therefore both of these iterations turn out to be order n square. So this might not seem much, but what happens is that every time we do this kind of a change, the total time required for your local search shrinks a lot, right? So for instance, I mean, and these are kind of relatively easy cases where you can reduce the time per neighbor. So my PhD student and I currently are working on a related problem where computing the time per neighborhood was taking order n4 time, okay, for every neighbor. And therefore when you reduce it, we reduced it by 2 orders of magnitude. And if you reduce it by 2 orders of magnitude, if you run the heuristics, local search heuristics, you'll find out that the improvement in time is amazing. I mean, it goes from several hundreds of milliseconds to several couple of seconds. Several hundreds of seconds to a couple of seconds, that is the improvement that you would see. Okay. So anyhow, when you're talking about this neighborhood calculations, one question which might arise is whether the size of a neighborhood matters. You know, if you have a small neighborhood, a neighborhood having a very small number of elements, then what happens is that among those small elements, there's a relatively less chance of finding a better solution. If you have a large number of elements, then the chance of finding a better solution in that large number of neighbors is higher. So on the flip side, if you have a large number of neighbors, then what you would have is a larger amount of time that you would require to compute all the solutions in the neighborhood and then find out the better neighbor. So the question is, does the size of a neighborhood matter? The answer is yes, it matters, but provided you can have a quick and easy way of computing the neighborhood and finding out the best solution. So to this kind of a thing, people sometimes talk about exponential neighborhoods or really large neighborhoods. Let's give you an example. So let us suppose that I have a traveling salesman problem with a very large, about 20 to 23 points. So, and therefore, let us suppose that this is one solution to the problem. So what is a really large neighborhood? A really large neighborhood can be, one way of looking at it is that if I take every alternate point, if I take, say, A, C, E, G, I, K, and so on and so forth, and then I look at mixing them up. So essentially, I take all of the points which are in the odd positions and then mix them up, I can get a neighbor. And now, if I have n points, then I would have n by 2 nodes to relocate, and each of these can be relocated in a large number of ways. So I would have order n factorial neighbors. So earlier we were talking about order n square neighbors, order n cube neighbors. Now here I'm talking about order n factorial neighbors. So you see, this is a really, really large neighborhood that I have. And so if I have this kind of a neighborhood, then it seems to be a great neighborhood, but it's very, very difficult to search all of these neighbors. So it turns out that if you are really smart about it, it does not take that much time. That was one of the very interesting results that people have found out here. So for instance, what they did was that they took this. So let us suppose that I have something like this, and I take every alternate point and try and remove it. So I take all these 3 points, and then I can put 2 here, I can put 2 here, I can put 4 here, I can put 4 here, and make all these kinds of combinations. Now, but what happens is that at the end of the day, I will have to put these 3 points in these 3 positions, right? So let us say that I have these 3 positions and these 3 points. So what would happen if I have to put the point 2 at this position? Then I would incur the distance of 1 to 2 and 2 to 3, distance 2 to 1 and 2 to 3. On the other hand, if I put this point 2 at this position, I would have to incur the cost 2 to 3 plus 2 to 5. If I put the point here, I would incur 2 to 5 plus 2 to 7. If I take the point 4 and put it here, I would incur 4 to 1 plus 4 to 3, and so on. So I know that for these 3 points, if I put it in these 3 positions, these are the costs that I would have to incur. Now you should have figured out that the best way in which I can put the points 2, 4, and 6 in these 3 places, or that is the way I can get the best neighbor, that exponential neighbor of the original solution, is to just solve a assignment problem on this. So if I solve an assignment problem on this, and I say that assignment problem says that, okay, this will have a assignment, this will have an assignment, this will have an assignment, then I know that I'll put 6 in point A, 2 in point B, and 4 in point C. And an assignment problem requires order n cube time. So therefore, if you have a large number of size of a traveling salesman problem, that kind of exponential neighborhood has a potential n factorial, order n factorial neighbors, where the best neighbor can be computed in order n cube time. So therefore, that was a neighborhood which is called the assignment neighborhood, the assigned neighborhood. The assigned neighborhood is one of a large number of neighborhoods that people have talked about, which are exponentially sized neighborhoods, but are computable in very reasonable time. Okay. So whatever happens, if you have a large neighborhood, there are some places where you can have these kinds of clever tools of computing the neighborhood, but most of the time, the computation is not that simple. So one method of looking at using those kinds of neighborhoods in a local search is to use multiple neighborhoods. You have a small neighborhood, which you can implement very fast. You take that neighborhood, and then this is a neighborhood. This is a neighborhood which can be computed very fast, and this is your primary neighborhood to use. And sometimes you have another neighborhood which is larger and which is more difficult to compute. The way you proceed is like this. So you start with a solution, then you use the first neighborhood, which is easy to compute. Keep on computing the neighborhood. And then you reach a solution which was the local optimum as per the first neighborhood. Then you bring out your second neighborhood. Your second neighborhood being a different neighborhood than the first neighborhood and occasionally being larger than the first neighborhood is very likely to find a point which was not there in your first neighborhood, but which is better than your current solution. Once you have this, you discard the second neighborhood and start with the first neighborhood again. You keep moving till you find out another solution which was locally optimal as the first neighborhood. Then you implement the second neighborhood. Find out whether you can get a better solution using the second neighborhood. But if you can't, so for instance, I use the second neighborhood and I find out that the local optimum is also the local optimum as per the second neighborhood, I stop and output that solution. So this is a solution that improves on the initial local search that you would have, and this is called a variable neighborhood search. This is a search method that is used quite frequently in solving hard problems. You have a small neighborhood, you have a large neighborhood. You use the small neighborhood to compute a locally optimal solution. Once you have the locally optimal solution, then you take that as the starting solution for the second larger neighborhood. Run an iteration of the second larger neighborhood. Remember, the second larger neighborhood is usually a neighborhood which is more difficult to compute. So you spend the time computing the large neighborhood and find out a solution possibly which is better than your original solution. Once you have that, discard the large neighborhood, go back to the small neighborhood, keep on doing local search. And you keep on doing these things, local search in various stages, till you find a solution which is locally optimal, not only for your initial neighborhood, but also for the larger neighborhood. Okay, so this is something which is called a variable neighborhood search. So this is one way in which you can make use of large neighborhoods in your local search without spending too much time. There's another way which is where you can use a large neighborhood, and that is really quite interesting. So suppose you have this, again, the same solution, and you have a large neighborhood. Now, also you have a small neighborhood which you can search very fast. Now, suppose you want to reach this point in your large neighborhood, right? If your neighborhood was this large, then this point was a neighbor of this point. But if you have a small neighborhood, you can see that I can take that small neighborhood and keep on having multiple iterations of that small neighborhood to reach the large neighborhood. So I can take the large neighborhood as all solutions that can be reached by, let's say, 5, by running the search with the small neighborhood 5 times, right? So if you do that, then you would see that that leads to a search which is called the Lin-Kernighan neighborhood search, which is very useful. So let's forget this for the time being, and let us talk about the Lin-Kernighan neighborhood search in terms of an example. So let us say that I have a solution from which I can take I can run different local search iterations and get to other solutions, the best solution in the neighborhood. And I plot that solution fed. Let us also say I'm solving a maximization problem where the higher the solution value, the better the solution is. Let's think about a knapsack problem. So in this case, what would happen is that I would start from this solution and then keep on making different iterations. So once I make different iterations, at some point of time, the best solution might be better than my current solution. In some other cases, the best solution may be worse than my current solution. I don't bother about this, I continue. So therefore, if I have the solution value, and these are the several number of steps that I take with the small neighborhood, let us suppose this is the maximum number of steps, okay? And these are the different solutions that I would get if I ran local search with the same small neighborhood multiple times. So sometimes I would get a better solution, sometimes I would get a worse solution. Okay. So if I have my local optimization, then my local optimization will stop here after one iteration. So from this solution, I found out a better solution. And if I look at the best solution from this step to the next step, the best solution has decreased in value. So I will say that this is my local optimum for my local search. However, if I run it for the max step, and then I find out that in this step, I have a solution which is better than everything else. So that is my local optimum for my Lin-Kernighan iteration. So what is a Lin-Kernighan iteration? A Lin-Kernighan iteration is I start out with my initial solution and then I go so many steps. For every step, I find out S prime, which is the best solution in the neighborhood of S. If that solution is better than whatever I've found so far, I will update my best solution. Otherwise, in a local search, I would have stopped. Here, I just move to the new solution, even if it is worse than my current solution, and continue. At the end of max step, I find out the best solution which I have received and which I have achieved in all these steps that I've run, and output that. So that is precisely what I have done. And here, this is something that we have talked about. It defines the neighborhood as a solution that can be reached through up to max step iterations. Now, sometimes people, what they do is that they'll say that if the solution that I've got is worse than whatever I started out with, you break. This is something that people occasionally use to make sure that the solution that you're getting is not too bad. It does not go to too bad a region. And yeah, sometimes that works, sometimes that does not. But that is the Lynn-Cunningham method. Lynn-Cunningham method actually started out a way in which we can deal with solutions which were worse than my current solution. If I was looking at variable neighborhood search, if I was looking at local search, both of those were looking at solutions which are better than my current solution. So, but the Lynn-Cunningham neighborhood search is the first search that talks about solutions which are worse than my current solution, but I'll still go through them because they have a chance of giving me a better solution somewhere down the road. Okay, so then let's talk about another algorithm which also assumes that, which also allows me to look at solutions which are worse than my current solution. Okay, so to do that, we start talking about a method that takes its motivation from physics. How does this work? So if you have looked at any metallurgical samples, you will find out that if you take a metal, there are different ways in which you can cool that metal. You can cool that metal very fast, you can cool that metal very slow. If you cool a metal very fast, it's called quenching. If you cool a metal very slow, it's called annealing, right? And if you look at the crystal structure of a quenched material and an annealed material, you'll find out that the crystal structure looks very different. Here, your crystals are very, very small. They are mostly imperfect. They are not joined very perfectly, right? Whereas if you're looking at an annealed structure, you'll find out that in an annealed structure, the crystals are much larger and they are joined very nicely. So which means that if you take a quenched thing and you hit a metal which has been quenched, it is much more likely to break than a metal which has been annealed, right? So in other words, the solutions that you're getting out here, the crystals that you're getting out here are not very well formed, or the crystals that you're getting out here are much more well formed. And you say that if you look at it from the point of view of an optimization algorithm, you'll say that these are bad quality solutions while these are good quality solutions. Okay, so therefore, what is the difference? Why does this happen in quenching and why does this happen in annealing? So what people say is that if you have a molten material, then the atoms of whatever metal, let's talk iron. The iron atoms are free to move in a molten metal. So once you cool it, then what happens is that the temperature, the amount of heat present in the metal is not enough for them to move freely. So they form lattices. So they form crystal lattices. Now, once you form a crystal lattice, sometimes you form a well-formed lattice, sometimes you do not form a well-formed lattice. Now, as you cool down the temperature, as you cool down the metal, what happens is that the amount of energy required to break the lattice and reform the lattice, that is not available as the temperature goes down fast, right? So if you're quenching, which means that your temperature is going down fast, then the first time you create a structure, crystal structure, that is the structure that remains. You have no way of modifying that structure to get a better structure. However, if you are cooling things slowly, the crystal structure has a way of breaking apart and then reforming the lattice, and doing this as long as it finds out that the lattice is not properly formed. Okay, so to take that intuition and put it in a solution method for optimization problems, this is what people do. People say that I'll do a local search, right? I have a solution, I find a neighboring solution. Now, if that neighboring solution is better than my current solution, I move to the neighboring solution, because exactly when you have atoms, as soon as they form a lattice, they're more stable, right? So if you have a solution and you form another solution which is better than your current solution, move to that solution. But however, if that current solution, if the new solution is not better than your current solution, then also you will move to that solution with a given probability, right? If it is not better than the current solution, then we'll move with a probability that decreases with the temperature of the process, which means that you are not going to get to a worse solution as you go further and further into the algorithm. Okay, so therefore, you are going to talk about a process. You're going to talk about a process where the option of going from a solution to a worse solution is possible, right? When you're forming a crystal lattice, breaking that lattice and going back to the molten stage is a solution which requires more energy, which is a worse solution. You allow that to happen, but that happens at a slower and slower rate the cooler your metal becomes. So therefore, you would allow that probability, you would allow that worse move to go through with a probability which reduces as time goes by. So that is what is called a simulated annealing. Okay, so therefore, let me not get too much into this. This is a method which, wait, give me 1 minute. Yeah. Yeah. So if I look at simulated annealing was a method which was very popular in the 1980s and 90s. They have kind of fallen out of fashion right now because there's a new way of looking at worsening solutions which seems to be doing much better than whatever the other methods did. And let's take a look at that method out here. Right. So let us suppose that I had a solution which was here, and I had a function f of x, and every time I would talk about a neighbor, I would talk about a solution which was one step to the right or one step to the left. Okay. So I'm talking about a function f of x which is defined on the set of integers. So if I talk about a function value of f2, its neighbors would be f1 and f3. If I'm talking about a function value at point 3, its neighbors would be 2 and 4. If I look at the function and I look at the function being defined this way, let us suppose and as usual, I'm trying to maximize that function. If you want to maximize that function, let's suppose I'm starting at this point, right? I could go to the left, I could go to the right. Let's say the right is improving, so I move to the right. Right. So when I move to the right, I could have moved from here to here, and then I could have moved down. To stop me from moving down, what I would say is that as soon as I move to the next point, I will ensure that I cannot move back. So I would take the solution and I say that I do not want to move back into this solution. Okay. So if I don't want to move back into the solution from here, the only way I can move is to the right. So let's suppose from here I move to the right, I stop moving back to the solution. So these two solutions are solutions that I will not go to. So therefore, if I can't go to this solution, the search that I have will keep on moving to the more and more to the right and will not move back to the left, even if the left was the best move at that point of time. Right. So if I do that, then this is a method by which I can keep on searching worsening solutions. Right. So let's see what happens if I, from this point, the next point I will go is here. And I say that I have not moved here. Now, at this point, if I were to find out the best solutions possible, the best neighbor of this point is here. Right. So if I did not remove these solutions from considerations, from here, I would go to this point. From here, the best neighbor would be this point. I would go here. So I would keep on oscillating between these 2 points. Now, what this method tells me is that once you have moved away from a point, don't move back again. Okay. So in that case, what would happen here is that I will not be able to go this way. I will have to go this way, even though the solution worsens. From here, I could have gone here, but this solution is not allowed, so I will have to keep on moving further. So therefore, one way of making sure that if I have a search, I can look at a large set of solutions in the search is to stop moving to other solutions which I've already seen before, right? So in other words, what I'm trying to do is to make sure that these solutions are forbidden for me once I've moved forward. Okay, another word for the term forbidden is taboo. So I can also say that in this kind of a search, I'm keeping on moving to moving on with the local search by marking everything that I've been to as taboo. Okay, but if you do that, you will find out that very soon you would run into major memory problems, because every time, every step you're going, you are keeping another solution in your memory. I do not want to go into this solution. So imagine after 500 iterations of this, your taboo list has 500 solutions. You cannot move back to any of those 500 solutions. So in the 501st iteration, the minute you have a solution that you want to move to, you will have to check all these 500 solutions and see whether or not you want to move to them. So obviously that is not going to be a very good method. So what people say is that, okay, I do not want to keep all these solutions. I will just make sure that I don't move back to a solution which I have gone to in the recent past. Okay, so let us suppose that I restrict the number of solutions that I will bar. How do I do that? I started out from here, and in the first step, I move from here to here. I've restricted this solution. From here, I will move here. So I've restricted this solution. From here, I have moved here. I will restrict this solution. Now you've seen that I have stored 3 solutions. Now from here, I can move only here. But if I move here, I will have to restrict this solution. But then that will make sure that I have kept 4 solutions in my restricted zone. So what I do is the first solution that I restricted, I unrestricted. Because from here, there's no way I can reach this point. Right? So now if I go one step further, I remove restrictions on this and add a restriction here and move further and further away. Okay. Now, even when I do this, what I see is that I have a large number of solutions that I'm storing. Is there any way in which I can even restrict and remove this amount of storage? The way I would do this is very simple. I would not restrict solutions. I would actually restrict the direction of move. So if I am at this point, what are my neighbors? My neighbors are this point and my neighbor is this point. How do I move this point and move to this point? I move one step to the left. How do I move to this point? I move one step to the right. Right. So therefore, what I would do is I won't stop storing, I won't store solutions, but I'll store moves that I want to restrict. Okay, so if I start from here, let us suppose from here I would move to this point, and then I would say I restrict the move which goes to the left, which stops me from going from this solution to this solution. Now, if I move here, I move right, I restrict myself from moving to the left. So every time I do this, all that I'm doing is that I'm not stopping a whole bunch of solutions. I'm just stopping moves. And storing moves is much easier than storing solutions. So imagine you're in an abstract problem with say 100 elements. So if you're in 100 elements, if you want to store a solution, you have to store the positions of the 100 elements. Now here, what I would say is that you don't exchange element number 37 with element number 52. So that is the only thing that I'm storing instead of storing a large solution that I'm restricting. So once I do that, that method is called restricting moves and not solutions is called taboo search. Okay. So how does taboo search work? Let us look at taboo search in multiple dimensions. Let's suppose that we have a 2-dimensional grid of solutions and we are looking at taboo search. So this is the neighborhood that we are looking at. And so if this is the neighborhood, then these are the 8 moves that we can talk about. Right. So if you have these 8 moves that you can talk about, then let us start with our original solution and take a look at the moves. Okay. Now, among these solutions in the neighborhood, I find out that this is the better solution. So if this is the better solution, I will move from this solution to this solution. How do I move? I move by going diagonally up. So therefore, what do I stop? I stop returning from to the original solution. So I say that this move of going diagonally down is restricted. It's taboo. So now marking that as taboo, I have moved to this solution. Now, since this move is taboo, going down, diagonally down is taboo, now my neighborhood does not contain all these 8 elements, but it contains only 7 elements, because this moving, if I had to move from here to here, I would have to adopt a taboo move. Right. Now, since this is not allowed, I will try and find out a better solution among all these other 7. And let us suppose that I found out that the better solution is to move vertically up. That means that I mark a move going vertically down as taboo. So once I moved here, I can't move here, I can't move here, because those will involve taboo moves. So these 2 solutions get restricted, and I am restricted to these elements. So if I am restricted to these elements, I can move, let's say I can move diagonally to the left. If I move diagonally to the left, going diagonally down to the right is restricted. So which means that when I'm looking at the neighborhood of this move, these 3 solutions go away, because this will, going here will involve this taboo move, going here will involve this taboo move, going here will involve this taboo move. Now, among these, let us suppose that the best solution that I have is to move to the right. So now if I have to move to the right, I will have to mark the move from here to the left as taboo, but my taboo list is filled. I had only 3 things that I could mark taboo. So what I do is that I take the oldest taboo restriction, remove it, and add the new taboo restriction. So my taboo list changes. So when my taboo list changes, I move here, and then I see that this move is taboo, this move is taboo, this move is taboo. So these 3 solutions are taboo. Then I look at all of these and I go forward. So if I move like this, the second taboo element goes out and I have a new taboo list. So moving this way, you see all that I'm storing are just a bunch of elements which I have marked taboo. Okay, let's see how this works in an abstract problem. Let us suppose that I have an abstract problem with 6 elements. And let's suppose my current solution is 1, 2, 3. Right. Now, the neighborhood that I'm looking at is a switch neighborhood. So if I look at a switch neighborhood, then I will see that these are all the neighbors of this solution. So here is a neighbor where I have switched 1 and 4. Here I have switched 1 and 5. Here I have switched 1 and 6. And here I have switched 2 and 4, 2 and 5, 2 and 6, 3 and 4, 3 and 5, 3 and 6. So this is my bunch of neighboring solutions. So once I look at these neighboring solutions, I can find out which is the best neighbor among this. So the best neighbor among this is, let us suppose, this solution. So therefore, from this current solution, I will move to this solution. How did I reach this solution from the current solution? By throwing out 2 and bringing in 5. So what I will do in my taboo is that I will not allow 5 to be thrown out, and I will not allow 2 to be brought in. These 2 are taboo moves, because that is precisely how I reached from my current solution 1, 2, 3 to my solution 1, 5, 3. So in my next step, my current solution is 1, 5, 3. So if I look at 1, 5, 3 and look at all the neighbors, these are all the neighbors. Now, if you look at this point, how is this point achieved? This point is achieved by throwing out 1 and bringing in 2. I can't do that. So if I can't do that, then this is taboo. Similarly, here, what is happening? I am taking out 1 and bringing in 4. That is not taboo. So this is quite all right. This is also quite all right. Now, what is happening here? Here, my 5 is coming out and 2 is coming in. Both of those are taboo. So I can't, this solution is not admissible. Here, 4 is coming in, but 5 is going out, and I've marked 5 going out as taboo. Right? So therefore, this solution is also not possible. So therefore, if I do not allow solutions in which 2 has to be brought in, these 3 solutions go away. If I don't allow 5 to be thrown out, these 2 solutions go away. So if I'm looking at my taboo list, if I'm looking at taboo search, the neighborhood of this solution are not all those 9 solutions, but only these 4 solutions. Now let's take a look at these 4 solutions, and then I find out that this is the best solution among them. How do I find out this solution? Here 1 has been thrown out and 6 has been brought in. So how do I do? I would say 1 has been thrown out, will be put it here. 6 has been brought in, will be exchanged with this. So 6 has been brought in. I cannot throw out 6 because 6 has been brought in, and 1 has been thrown out. I do not want 1 to be brought in again. So I remove that and add this. So my taboo list changes. So once my taboo list changes, I take this solution and that becomes my current solution. I again have my neighboring solutions. From my neighboring solutions, if I look at all the neighbors which involve one of the moves which are marked taboo, these are the ones that get thrown out. And I'll be left with only these 2 neighbors. So searching these 2 neighbors, I can find out which is the best neighbor and then carry forward. So this is how taboo search usually works in for optimization problems. Now, this is a basic taboo search. Now, there are multiple other things that you can talk about in taboo search. The most commonly implemented taboo search will have the taboo restriction and will have something called an aspiration criteria. The aspiration criteria says that if I have a solution which is taboo, but which is much better than any solution that you have reached so far, forget about the taboo restrictions and go to that solution. Okay, so that is a solution that I aspire for. It is much better than whatever I've got. So in that case, I will ignore my taboo restriction. Also, I can periodically stop my search and take a look at all those regions in the solution space that have not been explored so far. Okay, or I can periodically stop and look at regions carefully where I have found good solutions. Okay, so the first one is called aspiration, the second one is called diversification, the third one is called intensification. Okay, the basic taboo moves and things like aspiration, diversification, and intensification are the usual ways in which you improve your taboo search to find out good solutions. Now, there are a whole bunch of other material out here. I will not go into this material because I've run out of time. But the thing is that, as you understand, when you're looking at heuristics, okay, heuristics started out as a quick and dirty method of finding out solutions which were reasonable. But given the amount of computing power that we have, we can take these heuristics and then improve it to the extent that in most places, when you look at heuristics, when you look at the outputs of these heuristics, you will find out that they are very, very, very close to optimal solutions. Of course, when you have these heuristics, there's no way of guaranteeing that you have got optimal solutions. But if you're looking at practical problem solving, you want to find out a solution which is good. Okay. Academically, we are extremely worried about optimality, of proving optimality of a solution, that the solution that we'll get has to be provably optimal. In many cases, when you're really running against time, what you want is a good quality solution. If it is optimal, great. If it is not optimal, then also it's fine as long as the solution is good, right? So when you're looking at heuristics, what happens is that the whole study of heuristics is much more geared towards practical problem solving rather than theoretical problem solving. What we do when we work in the field of operations or when we work in the field of optimization is to go for a mathematical way of proving that the solution that a particular algorithm will give you is optimal, or I can give you a bound of the gap between that solution and the optimal solution. In practice, often these are methods that are used so that because they're easy to implement and you know that you're going to get a solution fast. So if you have a problem which is a kind of a strategic problem, which is a problem that you solve once in a year, once in 10 years, once in 5 years, you go for exact algorithms. They will take a lot of time, but the solution that you're going to get is an optimal solution. It is the best solution that can be. However, in many situations, you will have to solve problems which are complex, but where you do not have the luxury of time to come to an optimal solution. In those cases, it is all fine to look for solutions which can find out an optimal solution, look for algorithms which can find out an optimal solution very fast. But at the same time, in the interim, this bunch of techniques that we have are nice techniques to give you a decent quality solution in reasonable time. With that, I will stop the presentation. Any questions that you have? I'm willing to take questions right now. All right. I do not see anybody having any questions. So, okay, there are some questions in the chat. One of the questions is that does machine learning algorithms incorporate heuristics? Yes, machine learning algorithms are mostly heuristics. So if you're talking about machine learning algorithms, these are heuristic algorithms because they try and figure out properties of solution computationally. So there is nothing in most of these algorithms don't prove optimality. You can't prove optimality. So they use heuristics to, yeah, short answer is that yes, they incorporate heuristics. The other question that I had was that in case of traveling salesman problem, the productivity of points 1, 2, 3 will also matter. So if you're looking at traveling salesman problems, and I'm answering J.K. Sharma out here, if you're looking at traveling salesman problems is a problem which has multiple variants. Okay. So in fact, if you start listing down the variants of the traveling salesman problem, then you could possibly have a 2-hour session on the different variants. There are certain traveling salesman problems. There are problems called the price collecting traveling salesman problem, where what happens is that when you reach a point, you get a certain amount of benefit by reaching that point. So there are certain problems which are very much like traveling salesman problem, but where you also have to decide which are the points that you want to reach. Okay, because every point would have some gain that you would get, some benefit that you would get if you reach that point. But however, reaching that point would require you to travel along a particular path, which will take time. So therefore, it's a cost trade-off between the benefit that you get for reaching a point and the cost that you spend to reach that point. So therefore, there are certain variants of traveling salesman problem where the productivity of the point or where the kind of points that you would consider are extremely important. And as somebody points out, yes, that is called the orienteering problem. Okay, an orienteering problem is a special case of the price collecting traveling salesman problem. And any other questions since we started in global optima? Shomodip asks, since we strive to attain global optima, but often these heuristics we may use get locked into on a local optima, how do you solve this? Okay. There is the short answer is that at the end of the day, if you're using heuristics, there's almost certain that you're going to get stuck in some local optima. Okay, that is precisely why we say that when we are using a heuristic, we don't guarantee an optimal solution. We guarantee a solution that we often guarantee a solution that is locally optimal in some respect. And that is why what we do is that we just hope that we get stuck in a local optima that's a good quality local optima, that is close enough to the global optima for us to live by. As you said, finding out the global optimum is difficult for hard problems. And therefore, it usually requires a lot of time. And number two, it requires the methods that you use are very, very particular to very specific problems. So these are ways in which you can get a practical solution out of a problem. I don't know whether you understood Shomodip's question, but yeah, that's my take on it. Right. Okay. Thanks a lot for being here, and I'll say bye-bye to you.